Hello students, here is another session. This is on angular momentum, torque, and how it relates to rotational motion. So we've already looked at the basics of rotational motion and we are moving into angular momentum. Remember that angular momentum is just like linear momentum, except that it deals with objects that rotate. So angular momentum is the analog of linear momentum. So momentum of an object that moves in a straight line is called linear momentum, and the momentum of a rotating object is called angular momentum. That's the difference. And we will look at the relation between them. But before that, the basic relations that we have looked at are displacement is angle times radius. We looked at that. And when you have something that is rolling, like a tire, the center of the tire is actually not rotating. It's moving in a straight line. So the center of mass has a certain velocity. And that velocity is given by omega times r, where omega is the angular velocity of the tire. So that's the relation between linear velocity and angular velocity. Now we're looking at three different instances of this wheel or tire rotating. Number one, on the left side, imagine that the tire is just rotating in place, so it's not moving. It's like a bicycle which is kept on a stand and somebody is just pedaling, so the tire is rotating. Now in that case, and as shown here, of course, it's going to be clockwise. That's the normal direction in which you pedal, clockwise, looking from this side anyways. And you see that the linear velocity of the top part and the bottom part are exactly the same. That's when it's rotating in place. But imagine next that this tire is just moving without rolling. So it's like somebody sliding the tire, which normally does not happen, but just imagine. In that case, all three parts, the top, the center, and the bottom, all three have the same linear velocity. Now, remember that in the last part, the center absolutely did not have any velocity, linear velocity, because it was not moving, it was in place. Now, the third instance is where you're looking at both of these motions combined together. So now you have the tire rolling, and it's rolling. So that means it's rotating and the center is moving in a straight line. So that's when, when somebody is riding a bicycle, that's the normal motion of the tires. In this case, it's very interesting to note that the velocity of the point P, which is touching the ground, is zero. It's not moving at that instant. On the other hand, the velocity of the topmost part, called T here, is actually 2 times the velocity of the center of mass. So the bottom part is not moving, it's virtually at rest. The center of mass is moving with the velocity v calm, as shown in the diagram, and the top is moving with double the velocity. So that's a very interesting fact. Next, let's look at the kinetic energy involved in rotation. Especially the last part. If the tire is rolling, then it has 2 types of kinetic energy. Because the center is moving in a straight line, it has linear kinetic energy, which is 1/2 mass times velocity squared. And then, because it's rotating, it also has rotational kinetic energy, which is 1/2 I omega squared. So whenever you talk of an object that is rolling, whether it be a sphere or a cylinder or whatever shape it has, it will always have these 2 types of kinetic energy. And the reason is that the center will move in a straight line, therefore it has the linear kinetic energy, while the whole thing is rotating, so it also has rotational kinetic energy. Just remember that. Let's think about an object that is rolling down a ramp. How do we calculate its acceleration? What is the formula? That's what we're going to look at. You may remember that if an object is sliding down a ramp, I mean, it's not rolling, it's sliding, then its acceleration is given by g sine theta, if it's only sliding. But that's not the case here, because this is not just linear motion. As I explained, it's both rotational and linear. So let's try to find out a formula. Now, before you find the formula, we got to draw the free body diagram. And here is the diagram. We can imagine it's a sphere. The first force is its weight acting vertically down. The weight is acting vertically down, you can see, and that weight is resolved into its two components, one perpendicular to the ramp and the other parallel to the ramp. And that is what is shown there. And then we have the normal force acting perpendicular to the ramp up. And then this is friction. Friction always opposes motion, therefore it's against the movement of the sphere. So those are the four forces. mg is the weight. Let the angle be theta. From the use of trig, we know that these components are going to be mg sine theta and mg cosine theta. N is the normal reaction and F is the friction. So the friction force acting at this point actually creates a torque. And you know that to calculate the torque, we multiply the force with the perpendicular distance, which in this case is the radius. So that is the torque acting on the object. But torque is also given by rotational inertia multiplied by angular acceleration, I alpha. We also know that A, that's the relation between linear acceleration and angular acceleration. We know A is alpha times R, where A is the linear acceleration, alpha is the angular acceleration. So we can substitute for alpha. So let's make that the subject. So alpha is A divided by the radius. And you can now take that value and substitute it here in place of alpha. So F times R now becomes I times, in place of alpha, we put A by R. A by R. So let's call that equation number 1. Now let's focus on the force mg sine theta. We're trying to look at the forces now. So you have one force down the ramp, mg sine theta, and you have the other force of friction exactly opposite. So when you take the net force, you're going to get mg sine theta minus F. And net force is always what? Mass times acceleration, where m is the mass of the object or the sphere in this case. So now when we bring in the math, we'll get mg sine theta minus, we are substituting for F from equation 1. And I hope you understand why we have R squared, because this R will go to the denominator, making it IA by R squared. So that's what you get when you manipulate that. And then you get mg sine theta minus is equal to MA plus, when you take the IA by R squared to the other side. And then we see that A is common between these two terms, so we can pull that out. And that will give us A times M plus I by R squared. And on the left-hand side, we have mg sine theta. For now, we can make A the subject and get our formula. A is therefore mg sine theta whole divided by this quantity, m plus I by R squared. Now that's a very important formula to find the acceleration of any object that rolls down a ramp without sliding. Now you notice that we have the rotational inertia factored into this equation. And different objects have different rotational inertias. I mean, the formulas are different. So depending on what is given, we will have to use the corresponding formula for rotational inertia. Now, assuming that it's a sphere, for a hollow sphere, we know rotational inertia is 2 by 3 mr squared. For a solid sphere, it's 2 by 5 mr squared. So this formula can be used to get the acceleration of different objects. If it's a ring on the other hand, if it's a disk on the other hand, it's mr squared by 2. If it's a very thin ring, it's mr squared. So here I'm considering a solid cylinder. A solid cylinder is actually a disk. Because of the way it's rotating, the axis of rotation is the axis of the cylinder. So it behaves like a disk, and rotational inertia of a disk is mr squared by 2. So in place of I, I'm going to substitute mr squared by 2 because we're considering a solid cylinder, which is a disk. And then when we do that, we will see that the mass is now available both in the numerator and the denominator. Therefore, it's going to cancel out. And we get A is equal to mg sine theta divided by m times, I've taken out the mass before cancelling it out. I could have cancelled it out. 1 plus half, because you only have half there since we took the mass outside. That will give us 2 by 3 g sine theta. So the acceleration of this disk or cylinder is independent of its mass. It's independent of its radius. It doesn't matter how big it is. It's independent of the mass, independent of the radius, and only depends on the angle of the ramp. Isn't that interesting? Next, we move on to the definition of a torque. We've already looked at this in the last chapter, but just as a review, torque is the cross product of radius and force. And cross product is usually written as the product of the two terms times the sine of the angle between them. Remember that R and F are vectors, and so we multiplied with the sine of the angle between them. That's a method of finding the magnitude of the torque. So now we come to angular momentum. I told you that angular momentum is analogous to linear momentum already. But here's the definition. Angular momentum is another cross product. It is the cross product of R and P, where P is the linear momentum. Therefore, angular momentum is sometimes called the moment of momentum because it's the cross product of R with P. And what is P? P is mass times velocity. So you can take that mass out and you can also write it as mass times the cross product of the radius and the linear velocity. That's one way of putting it. And always understand that whenever you take a cross product, whatever you get would be perpendicular to the plane containing the other two. That means in this case, if R is this way as shown in the diagram and P is this way, you see that they both lie in the XY plane, then the result of the cross product, which is the angular momentum, as you can see, is perpendicular to that plane. That means it's along the z-axis. That's a very important rule. That's why we use the right-hand rule in all these cases to find the direction of, in this case, angular momentum. And according to the right-hand rule, if you stretch the if you stretch your right hand, let's see if you can see it. If you stretch your right hand with R, I got to incline a little bit more, with R shown by the fingers, and your palm showing the direction of P, R and P, then the thumb gives the direction of angular momentum. See that? R shown by the fingers, your palm showing the direction of linear momentum, then the thumb gives the direction of angular momentum. This is the right hand rule. Now therefore, if you imagine that R is kept the same, but if the linear momentum is exactly opposite, then I would have to rotate my hand, and you see what happened. Now the angular momentum is also in the opposite direction. So you should be able to use the right hand rule to find the direction of any cross product or any vector which is given in terms of a cross product. All right, here is a table that shows the relation between linear and angular quantities. First of all, force is dp by dt. Force is the rate of change of linear momentum, and similarly, torque is the rate of change of angular momentum. And then in place of force in linear motion, we have torque in rotation, as you can see. And then linear momentum is analogous to angular momentum, and formula for L, as we looked at, is R cross P. But they can also be written as, linear momentum is mass times velocity. Angular momentum is rotational inertia times angular velocity. Wherever mass appears in linear motion, we are going to have rotational inertia in rotational motion. And then since we have the law of conservation of linear momentum, similarly we have the law of conservation of angular momentum. Now, the law of conservation of linear momentum came with a condition, and that condition was that there must be no external force acting on the system. When it comes to, angular momentum, there is a similar condition. But guess what? What are we going to have as the condition? We're going to say there's no external torque acting on the system. So that is the law of conservation of angular momentum, which states that the total angular momentum is a constant. That means the total initial angular momentum is the same as the total final angular momentum, which we see there, which can be mathematically represented like this. And right there you see the condition. It's an isolated system. That means there is no external torque acting on the system. Let's try to work out a few problems. Here is a good one. In the figure, that's a figure here, a solid 0.3 kilogram ball rolls smoothly from rest, starting at a height h, which is 6.4 meter, until it leaves the horizontal section at the end of the track. So that's the horizontal section at the end of the track, and that's at a height little h. How far horizontally from point A does the ball hit the floor? So the ball is going to come rolling down, and then it's going to go off with a horizontal velocity because that part is horizontal, and it's going to fall somewhere here on the floor. So we are asked to find out that distance. Now, how do we do this? What's the plan? You're given the mass of the ball, you are given the two heights, that's all. Nothing else is given. And immediately your brain must go towards thinking in terms of energy. Because at this point, the ball has potential energy. As it comes down, it loses its potential energy, some of which changes into kinetic energy. And at this point, it has a little bit of the potential energy remaining, but now it also has kinetic energy. And according to the conservation of energy, the potential energy here should be equal to the sum total of the potential and the kinetic energies at that point. That's the first thing. The second thing is that I mentioned when I was explaining it that at this point, because this point or this part is horizontal, the ball is going to only have a horizontal velocity when it goes off. It will not have a vertical velocity at the point it leaves that ramp. Those are the two important points. So let's apply the first one, law of conservation of energy, which says mgh. I should have used mg times capital H. Okay, mg times capital H, because that's H there, is 1/2 times mass times velocity squared plus 1/2 I omega squared. Oh, do remember it has both kinds of kinetic energy. It's rolling, isn't it? So it has rotational and linear kinetic energies. And also omega is V by R, and I, because it's a solid sphere, it's a ball, so it's a solid sphere, is 2 by 5 mr squared. Now this is just a preliminary step which you're going to apply in this condition. That's why I did not put caps H there. Now I've done it. So kinetic, the potential energy, I mean, at the top is the total kinetic energy at this point plus the remaining potential energy, which is going to be mg times small h. So that's the fundamental equation that we were talking about. So that's 1/2 times mass times velocity squared, and because it's a solid sphere, I is 2 by 5 mr squared, which we're going to use there. So 2 by 5 mr squared. And we're also going to use omega is V by R. Both of those, and so let me just move this a little faster, okay? V squared by R squared plus mg times small h. So we get all those. The 2's get cancelled, the R squares get cancelled, and here you have 1 by 2 plus 1 by 5, which is 7 by 10. So that's how I get 7 by 10 plus mgh again. 1 by 2 plus 1 by 5. And then we have mv squared here, and also mv squared here. So all I got to do is add 1 by 2 plus 1 by 5, which gives 7 by 10 mv squared plus mgh. And then here is the velocity. Velocity is, when I rearrange this, take this term to the other side and flip this and make velocity the subject, that's what I'm going to get. 10 by 7 g times h minus h, given as 6.4 minus 2.1, and you get the velocity. This is going to be the horizontal velocity with which the ball is going to roll off, right? Okay. And so we'll have to use kinematics now. We know that the height through which it falls is little h. So we can use that height. We know that the acceleration is going to be the acceleration due to gravity. Use both of those in this equation to find the time. So I've already made time the subject there. A square root of 2h by g. In place of y, I've substituted little h. And you get the time. Once you get the time, you multiply that time with the horizontal velocity to find x. Isn't that what we've been doing? Yes? So plug in the numbers and you are going to get the answer as 5.1 meter. That's what we get. So here is the next one. The rotor of an electric motor has rotational inertia 8.42 times 10 to the negative 3 kilogram meter squared about its central axis. The motor is used to change the orientation of the space probe in which it is mounted. The motor axis is mounted along the central axis of the probe. So you have the motor and you have the probe. The probe has rotational inertia 13.8 kilogram meter squared about this axis. Calculate the number of revolutions of the rotor required to turn the probe through 22 degrees about its central axis. So from the question, we know that the axes of both are the same. We are given the rotational inertias of both the motor and the probe, and we are asked to find how many revolutions the rotor has to make to turn this probe through 22.0 degrees about its central axis. So what is the idea here? Well, of course, it's a conservation of angular momentum. So let's use the conservation of angular momentum. And what is that? That I times omega is a constant, which means I m omega m is IP omega p. Take the integral. And you know why we're taking the integral? Because we know that omega dt is nothing but theta. Same thing on the other side. So that you have theta m, the angle rotated by the motor on one side, and on the other side you have the angle rotated by the probe. And Im and Ip are constants, that's why they were taken out of the integral. So integral omega dt is theta m, integral omega p dt is theta p. Rearrange that. When you rearrange that, you get theta m in terms of theta p. That is so simple. We're given the values of Ip and Im. That is Ip. And then we have theta. We can keep it in degrees in this case, because if you keep the angle in degrees, you're going to get the other angle in degrees. If you change it to radian, which is not necessary here, you're going to get it in radians. So better keep it in degrees. So when you work out that, we're going to get 36,100 degrees. And the number of rotations, you know, one rotation is 360 degrees. So just divide this by 360 degrees and you will get the number of rotations. Divide that by 360 to get about 100 revolutions. So the motor had to turn through 100 revolutions just to turn the probe through 22.0 degrees. So that is how it works, because we want to turn the probe through an accurate angle. So that's why the motor has to turn through such a lot to just turn the probe through 22.0 degrees. I hope that makes sense. Let's look at the next one. What do we have here? Okay, so this is kind of moving very slowly. So a marble is rolling without slipping across the floor at a speed of 9.6 meter per second when it starts up an incline at 31 degrees to the horizontal. A. How far along the plane in meter does the marble travel before coming to a stop? And B. How much time elapses while the marble moves up the plane? So did you get the situation? A small marble is rolling without slipping across the floor at a certain speed given here, and then it comes to an incline. So because it already has energy, it's going to go up the incline and then it stops after it moves through a certain distance, which we have to find. The angle of the incline is given. So we've got to find both how much it moves up the ramp and how much time it takes. So we already did this part. That's why I've just written it. For a sphere, we know that the total energy turns out to be 10 by 7 mass times velocity squared from a previous problem. And that now becomes the potential energy. The total kinetic energy now becomes the potential energy when it stops. So you can easily rearrange that to make H the subject and calculate the height. Okay, so that was 7 by 10. So obviously something miscalculation there, and you get that. Next, you're asked to find how much time elapses while the marble moves up the plane, for which we need to find the acceleration of the marble, which we know. We know the formula is mg sine theta divided by m plus I by r squared, okay, which we derived. So using that, we can find the acceleration. We know that we do not need the mass because the mass will get cancelled out. And we are using 2 by 5 mr squared again because this is a solid sphere. So it's a marble. And then you only have g sine theta by 1 plus 2 by 5. 1 plus 2 by 5 is 7 by 5. And on doing that math, you get the acceleration. All right, so 4.21 meter per second squared is what I have for the acceleration. Then we can use kinematics to find the... Oh, I think I did not do that part. How much time elapses? Would you be able to do it? Of course, using the kinematic equation. Because we have A, we have T, we have the initial velocity also. We have the final velocity. So because of all these terms being available, you can use the kinematic equation, and please calculate it because I just forgot to calculate the time. Here is the next question. So you're given two vectors, you're given R and P, and we are asked to calculate the angular momentum. How do we do that? If you're given, well, it could have been that way, or this question is actually giving us R and F, and we are asked to calculate the torque. So how do we find the torque? Torque is the cross product of R and F. So we got to know how to take the cross product of these two quantities, these two vectors. And this is just a review for those who already know. Torque is the cross product of R and F, and the order in which you write those two matters, because R cross F is negative F cross R. So put it as R cross F. So we put the IJK, and then we write first the coefficients of R, because the order is important. 4, 3.5 and 6. And then below that, you put the coefficients of force. I, there is nothing, that's why it's 0. And then you know how to take the cross product. To find the coefficient of I, you go 35 times negative 4 minus 6 times 9. Let's do that. So the coefficient of I, 35 times negative 4 minus 6 times 9. Okay? And when you come to J, you have to put it as minus J always, and then 4 times negative 4 minus 6 times 0. All right, so if you put plus J, like I did, then you'll have to reverse the direction in which you go. You'll have to go 6 times 0 minus 4 times negative 4. You can do it either way. It's better to put a negative and then keep the order the same. Left to right minus right to left, okay? Or the same thing. If you want to put a plus, change the order. Go right to left minus left to right. Hope that makes sense. And then when you come to K, just put plus K and go 4 times 9 minus 35 times 0. I'm just showing these products with 0 just so you can see it. Because if you multiply anything with 0, it is a 0. Negative 68. It actually gives you negative 68. Let's check it. Yep. Because it's negative 140. Oh, it's 3.5. That's why. That's why I made it. It's 3.5. Look at that. So, negative 54 and negative 14. So that's why you get negative 68. All right. So we get the torque. How do you get the torque as 78.6 meter Newton? Well, do you know how to find the magnitude of a vector? Yes, you do. It's square root of the sum of the squares of the coefficients. So in this case, square root of 68, negative 68 squared plus 16 squared plus 36 squared, it will give you 78.6. And then what if you have to find the angle in this case? Now to find the angle between R and F, how do we find the angle? We got to go to the dot product. Now how is the dot product defined? The dot product of two vectors is, in this case, R dot F is equal to R F cosine theta. So if you rearrange that, you can get cosine theta as R dot F divided by the product of the magnitudes of R and F. See, that's what I've written. So that's just rearranging it. So in this case, when you take the dot product, it's easy. You only take the product of like terms. There's no I here, so it's 4 times 0, which is 0. And when you look at J, you have 9 here and 3.5. So when you multiply these two, you get 27 plus 4 31.5. You get 31.5 and then minus 24. See that? Minus 24. So 31.5 minus 24, which gives 7.5. And that is what goes here. So 7.5 divided by the magnitudes of R and F. Again, how do you find the magnitudes of these two? I've not done it, but you know, 4 squared plus 3.5 squared plus 6 squared. Add all of them, take the square root. That gives you 8.02. And similarly, 9 squared plus 4 squared, square root of that gives you 9.85. So that's how you take the magnitudes. And I think I'm writing that again here. Yes. And you get theta when you take the inverse of whatever you get here as 84.6 degrees. That means the angle between these two vectors is 84.6 degrees. Let's move to the next one. A disk with a rotational inertia of 2.46 kilogram meter squared rotates like a merry-go-round while undergoing a torque given by tau is equal to something given there. At time t is equal to 1 second, its angular momentum is given. What is its angular momentum at t 3 seconds? So you have the rotational inertia, you have the torque, and remember the torque is a function of time because it depends on time. And so basically you're looking at the relation between torque and angular momentum, which we know torque is the rate of change of angular momentum. Tau is dl by dt. Okay, and since we are looking for angular momentum, angular momentum is made the subject, and so you're going to get integral tau dt. And then put in the function given, which is 4.13 plus 2.85 t dt. Integrate that expression. And it's a very simple. You know that when you integrate, if you're not given the limits, there will be the constant of integration. The constant of integration is the boundary value. In this case, it's the initial angular momentum. Whatever the angular momentum was when time was 0 seconds or 1 second. In this case, it's 1 second. So we put the constant of integration as L sub naught or L naught. And then whatever we have there is integrated. That's going to give 4.13 because integral dt is t. And this is going to give you 2.85 t squared by 2, which is 1.43. Next, we have to find the constant of integration. So when t is equal to 1 second, we're given that the angular momentum is 2.37. We can use those two numbers in this equation to find L naught. So we know that L is equal to that. So 2.37 is equal to L naught plus 4.13 times t is 1 second. You're substituting that. So plus 1.43, 1 squared doesn't make a difference. 1 squared is 1. Okay. Now rearrange all that, do the math, and you will get negative 3.19. Now we go back to the function, and we can just use that same function to find the angular momentum, because we already got L naught and we have that relation. So now plug in the value of t as 3.00 seconds and do the math. So t is 3.00 seconds, and you're going to get something. All right. Simple algebra, whatever you get. So this is more important than the math always is the idea. The idea here is the relation between torque and angular momentum. If you're given angular momentum, you can find torque by using tau is equal to dl by dt. But if you're given the torque, as in this case, you can find the angular momentum by integrating. So that's the essential idea. The answer is 22.0 kilogram meter squared per second. And that, I think, concludes this short video on angular momentum, its relation to torque, and how we use that to work out problems. Remember, if you've got here and you're watching this video, remember to watch the previous one on rotational motion. And this is just a continuation of that chapter. Thank you very much for listening in and trying to understand physics. So until next time, this is me signing off.